Nanofabrication technology is going even smaller than MEMS fabrication or microfabrication technologies. And so now when I look at the relative sizes, we're looking at to the 10 to the minus 9, 10 to the minus 7 type nanometers, right? So very small sizes. So where do we apply this and what kind of feature sizes we're talking about? They include films, coatings, dots, lines, tubes. Nanoscience is concerned about the study of structures in that size of 1 nanometer to 100 nanometers. Nanoscale refers to the dimensions of nanometer there on the top. So what are some examples at that scale? You're looking at helium atom, you're looking at proteins, you're looking at flu virus, red blood cells. Those are the kinds of, we're trying to target that type of size, which is incredible. Think about it. So what is important of being able to achieve that size? The important is that if you can achieve that size, you can pack a lot more, number one. But as you do that, things become more complicated. What I mean with that, as you achieve smaller sizes, the surface properties at that scale become a lot more important. There's two types of approaches that we use for nanofabrication. The first one that we want to take advantage of were covered previously in chapter 2 earlier on in these lectures. And the first one was primary bonds. So you can take two atoms to create a molecule, and then you have a secondary bond where you take two molecules and you bring them together to be able to fabricate a bulk material. So secondary bonds is one approach that we can achieve nanofabrication. And how do we achieve this? How we can get to that level? We take advantage of quantum mechanics. That's a branch of physics that concerns with the notion that you can use energy to be able to influence and manipulate objects at that small scale. How we account for this? How do we achieve this? What's the conduit to this? Electricity. We use that, and we use electrons to make that happen. We also look at using light by using photons. Remember, photons are the approach to be able to transmit light, while electrons is the means to transmit electricity. So quantum mechanics is what we leverage to be able to achieve nanotechnology, and that's what we will be talking about in few slides here. So the first one I want to talk about is microscopy. So with this approach, you're looking at being able to achieve magnifications of 1,000 times, a resolution of 200 nanometers. The next one here is electron microscopes. Here you're looking at magnification of 1,000,000 times with resolutions of 1 nanometer. And then you have scanning probe microscopes, which we've used quite a bit, and that can provide you magnification of 10 times greater than electron microscopes. So it's even greater than above. So yeah, very impressive stuff to be able to achieve that. And this is what has allowed us to be able to see atoms, right? That's how we've been able to see that. So STM is a scanning tunneling microscope. You apply voltage to the probe. That causes, and I'll show a picture. I have a picture. It's going to cause the electrons on the surface to kind of tunnel up. And I'll show you that as you bring the probe tip, it's going to kind of cause the electrons on the surface to kind of take a shape. The tunneling electrons, you can measure that with current. And as you move that probe above the surface, I'll show you a picture, then you're gonna be able to manipulate the location of the surface atoms. And the variations in the currents that you apply can then start creating topological graphs or maps at that scale. So here's example. Here's your scanning tunneling microscope. Here's your tip. And here in the surface, I have electrons. And I'm using that approach to be able to study that surface. And that information is then amplified, and then you can then project that into a display. You also have something called the atomic force microscope. Much more impressive. You have, this is quite incredible to me. You have a cantilever beam that deflects due to the forces being exerted by surface atoms. And as you're doing that on the surface, you're able to measure contours of the surface, any roughness on the surface. You can also create a topological graph of the surface too, similar to before, and it's quite impressive that you can use a cantilever type beam to measure this. Here's an example. You can see an IBM Nano being imprinted that you can see the cantilever beam here, for example, measuring what's going on the surface. You have your laser pointed on the cantilever beam. And as that's deflecting on the surface, this laser is going to send different signals into the photodiode, which is then going to send a signal onto a digital display. And what's impressive here is IBM here, this size here is in the 20 nanometers. And I'm able to use this atomic force microscope to be able to actually tell you what it actually says, which is IBM Nano. So really impressive what we can achieve. And by the way, these letters are written in silicon oxide, which is what we talked about earlier in the electronic circuit, integrated circuit class. So with nanofabrication processes, there's two ways to look at this. There's a top-down approach and the bottom-up approach. The top-down approach basically uses the microfabrication techniques we discussed before, and then you apply that, you scale it up or scale it down. You scale it down to the nano level. And then you have your bottom-up approaches, which is how you can manipulate the atoms and molecules to achieve what you want. So top-down approaches, I already kind of covered it here. You're going to use your rubber flat mold to push on the resist. That's going to cause your pattern. You're going to remove that pattern using the approaches we already covered. But when you look at nanotechnology fabrication techniques, is going to be based on what we covered already, lithographic technologies. But now you're going to look at extreme UV light, down to the 13 nanometer level, to be able to achieve a lot of this. And remember, the way we remove the resist layer, we use masking and we use etching, if you recall. And that's what's going to allow us to create the shapes that we want on the silicon, which is the material that's semiconducting. And this is called soft lithography from the previous lecture we discussed. They're here in the bottom. Bottom-up approaches, you start with looking at how you can manipulate some of these atoms and carbons. So let me show you an example of that. How can I do the manipulation? Which I've been talking about quite a bit. You have to be able to achieve this, you have to be able to do this in vacuum environment, high vacuum environment. Normally the surface has to be brought up to a temperature near 0 Kelvin to be able to make that happen. And why we do that is to reduce the amount of thermal deficit. The problem with this technique is very slow and it's very expensive. On the right, what you see is surface atoms are present. And I bring my probe tip coming closer to it. And as I do that, as I bring it down, there's some distance between the probe and the surface. And that distance is sufficient to prevent any movement of the atoms in that level. But as I bring that tip down, I'm going to start attracting certain atoms. And that's going to help me start shaping what I want to shape. So these approaches have been used massively across industry. What I want to go up and show you here is self-assembled monolayers that we use. It's called SAMs. So here I have molecules that are attracted to the surface. So I have these molecules they're kind of like disorganized. They get absorbed onto the surface, and then they will start forming islands. And then the islands will grow onto the surface completely covered. This approach is called self-assembly monolayers, and this tends to be like one molecule thick, very thin. You can also do multi-layers if you wanted to. Okay, we're using energy in this case to make that happen. You then have this other idea called carbon nanostructures or fullerenes. You can create something even close to a soccer ball in that scale. You have 60 atoms typically assembled together. They're shaped like that. It has electrical properties of an insulator, and it can also become a conductor. They're looking at possible uses of this in the medical industry. They also think that this could be used for attaching, you can attach it to drugs to go after something particular. But yeah, very interesting approach. You can create other shapes, like an armchair is here in the top, here left. You have the zigzag here, and then you have the chiro. So 3 different shapes can be created. And by the way, these structures have a huge elastic modulus and tensile strength, much greater than steel. And also you can play around with these structures to be able to achieve particular conductivities, properties. So how you produce carbon nanotubes, laser evaporation method is one, carbon arc technique is another one, and chemical vapor deposition. So those are 3 techniques that people have used industry to be able to achieve this. So where do you see nanotechnology products in real life? Cosmetics, sun lotions. I don't know if you worked on waxing your car or, but that's using nanotechnology there. Coatings, like my glasses here has a coating. That's using nanotechnology to achieve that thin film that I want. Scratch resistant paints. So yeah, those are some of the applications. And a really nice area to be studying today is here at the bottom, nano robots. Those are nanoscale machines that can actually perform operations. They can have intelligence, they can actually grip things and can achieve things that were not possible before. So that's a very strong area to pay attention to. With that said, that concludes today's lecture. Very top level.